Hello, it's Keith here, and this is day 5 of the Grime Z80 programming project. So how are things going? Well, let's take a look. So we start on the 5200 here, the Atari that is. And you can see basically the game is now hopefully working okay. I think we had the Grime in yesterday, didn't we? But I can now die, and you can see we've got scores. And we've got the title screen working, and I think all of the game logic code is now in and should be working in exactly the same way as it did on the other systems. I've been doing some bug fixing with the sound as well. I think the sound was in reverse, the pitches were backwards on some of the systems just because of bugs in chibi sound, so I've fixed that as well. But I mean, really everything's hopefully okay now. My random number generator is a bit poor, which is why you saw the Grime didn't descend very neatly there. So maybe I need to do some more work on that. Unfortunately, I was using the R register on the Z80, but there isn't an R register on the 6502. Now, I'm sure that there are ways on each system of it reading sort of relatively random noise, maybe from sort of analog ports and things, but I don't currently have any strategy that I've got planned for that. So at the moment, oh, that's interesting. Oh no, I thought it was at the bottom of the screen. I thought it should be dead. No, it's alright, it's working okay. But I don't have any real good plan for that at the moment. So at the moment I'm picking a random byte from the source code and then XORing in some of the other registers and XORing the previous random value. But it's obviously not working that great because, as you saw there, it's not really that random. So maybe I need to do some more work on that. If I've got memory, I could use a lookup table maybe. Anyway, so you can see the game's working okay there. I've also done some speed improvements on the graphical code for the Atari 5200 and Atari 800. Let's just check it still works on the Atari 800. Of course, they are basically the same system. Now, one thing I do need to do with the Atari 800 is fix up the sprites a bit because they're pretty nasty at the moment. But that's kind of what I'm going to be doing next over the remaining 2 days. That's one of the things, at least. Now, talking about nasty sprites, I think the Apple II can beat us for nasty sprites, but at least it's functionally working. I've done no optimization at all on the Apple II graphics, so well, I've done optimization in the code, but not in the actual sprites themselves. So you can see that they really are pretty terrible. But it's actually the frame rate's a bit slow. I need to maybe reduce the amount of animation here. But maybe I can also do some optimization on the code as well. But I mean, you can see that the game logic is working. And I've also been doing some work on centralizing the text on all of the systems. Because even on the higher resolution systems, I'm emulating a 256 by 192 screen. So everything is positioned for that. So you can see that the text is in the corners. I've been doing some optimization to the graphics code of the BBC, so it may be a bit fast today. I said before I optimized the C64 and the BBC could benefit from the same optimizations. Well, I've now made those optimizations, so you can see the game's running pretty crazy fast here. I've also been doing some general tidying up of the code, just trying to make the code as small as possible. When I did Grime Z80 originally, it was just the 7-day project, but with Grime 68000 and 6502, that's interesting, why is that not being deleted? I'm planning on using the code in a future project, so it's not just a case of just getting Grime 6502 to work. I actually want it to be as efficient as possible, both in terms of speed and in terms of size, because as I've said, some of these systems are very limited. The BBC's only got 32K, that's the BBC B as well, and half of that's actually used by the screen memory. So, you know, coding, it has to be really efficient. So I've been trying to make this code as small as possible, reusing functions, making sure everything's efficient. It's beneficial both ways because small code tends to be fast code in most cases, because if you're using the 0 page it takes 2 bytes, but if you're using the internal registers it only takes 1 in most cases. So it benefits both ways in some cases. But as I say, I need to try and make the code as small as possible so I can make more use of it in the future. So I think the C64 has had some slight improvements over yesterday speed-wise. I mean, in a lot of cases, I'd kind of done everything I could, but in a few cases, I think there were still a few things that could be improved. The color drawing code, because the C64 is basically a black and white system with color attributes. It's for color, but they don't have a defined color until you define them in the color attribute tables. So that color attribute code hadn't been optimized before, I don't think, and now it has. So maybe it's still a little bit faster, but you know, I'm still going to be optimizing for 2 days, so we'll probably scrape a bit of extra speed out of everything anyway, but most of the speed benefits have probably already been achieved. Now, one system that definitely doesn't need speed benefits is the Atari Lynx. I am actually having to slow it down to make it playable. As you can see, the screen is still blooming tiny. I'm still thinking of doing that 6-pixel tall tile thing. I think that might be worth doing, so we'll see how that goes. But as you can see, the game is playable fine, and it looks good, obviously, because it's a 16 colour system. And as I said, I'm massively slowing down. I'm struggling to even get the thing to turn around properly. I've had to massively slow it down because the system is so fast. So there we go. Graphical glitches maybe there. I don't know. Anyway, so that seems to work okay. Now onto the NES. Now the NES, as I said before, has got this speed issue because of the way I'm redrawing the screen. I was having some trouble figuring out which controls to use. So you can see the game is running very fast, but the frame rate's quite poor, and that's because, as I said, I'm only updating part of the screen each refresh on the NMI interrupt. So during the VBlank, so that's why you've got that poor frame rate. Now what I'm thinking of doing is changing it so that it has a queue of commands, and so rather than updating all of the screen, it only updates what's changed. Now the disadvantage of that will mean it will limit me to how much of the screen can change each frame, but the advantage is I think for this game it will be faster, but I do need to rewrite that. PC Engine has no such problems. PC Engine is very fast. Of the 6502 systems, I guess it's probably the best one if you don't count the Super Nintendo, but it's got 16 colour, it's very, very fast. This is heavily slowed down to make it this playable, and it's got a nice big screen, so you know, very nice system. Some trouble rotating my player there. Maybe I need to put some debouncing on the rotation or something, I don't know. Anyway, you can see it works fine. And on to the next one. Super Nintendo. Now the Super Nintendo still has some graphical glitches as before, but I have managed to improve them a little bit. If you remember before, we were getting some sprites on the screen when the screen was supposed to have cleared. I've reorganized the commands a little bit with regards to the VBlank, but now you can see you've got the opposite problem where things that should have been cleared actually aren't. So it's still not right. I do need to write some kind of interrupt based screen updating routines, because we say what we've got here is okay, but it's not perfect. So that's one of the things I do need to look at over the next 2 days. Finally, the VIC-20. Seriously, need to rethink that web address there, don't I? It's not fitting on the screen. I hadn't noticed that up until now. So anyway, we'll get that fixed. I think we can cope with that. But I mean, the game code works fine, but the game code is common to all of them, of course. It's only the graphical routines that are actually different. So that's how you make a game this fast on this many systems. You use common code where you can, and you use platform-specific code where you can't. So that's the trick. Anyway, that's enough of that. Let's have a look at some of the code. So, you know, I mean, a lot of things are changing along the way, and as I said before, I'm going to go over the entire source code on the last day, on day 8, which will be done shortly after the end of the project because I need a rest. So anyway, I thought we'd have a look at the player dead code today because that's a new piece of code. Of course, it's been converted from Z8 again, and let's see what I've been doing. Well, the first thing is I've been adding some extra shortcut functions So you can see here there's a command called load pair, which is the equivalent of loading BC with a word here. So this is a macro again, and it's just the equivalent of using the low byte here and storing it into 0 page register A, and then taking the top byte and loading it into A+1, because the pairs are in reverse endian, so the lower value one is first, the larger value one is second, and that's what the values need to be in the 0 page for it to work correctly. I've also created a one called load 1, again just as a convenience, so this just loads a value in. And I've also created a one called add pair, which is the equivalent of an add BC, DE, but I no longer need to fill one of the registers, like the DE register in that case, with a value. So it actually saves me some processing time. And this is inline rather than a call. So it maybe takes a little bit more memory, but I'm not sure if it actually does, because in some cases the commands, all the loading commands are so big. I mean, look how big they are. So I think it's actually probably smaller as well. So that's something I've added. I've also, as I said, about increasing efficiency with regards to making the code smaller, I've added this CLDIR command, which is a clear load dir. Now, if you remember from my Z80 tutorials, you can use the LDIR command to clear a bank of memory. What you do is you set HL to an address, DE to the address +1, you 0 HL or set it to 255 if that's what you want the range to be filled with, and then you set a byte count and it will copy from what it just wrote to, and that will effectively fill the entire range. And CLDIR is my function doing that. So it's effectively setting DE to HL +1, setting HL to whatever byte is in the accumulator, and then it's just running the command. And so this saves me time setting DE and setting that default value by default, because I was having to do that in various places, like clearing the screen, forcing a refresh of the screen, clearing the data areas at the start, and even things like filling the color memory on the C64 by default. So this is allowing me to do a fairly common command that otherwise would take quite a lot of extra commands, and I can use this to save time programming wise and save data space in the code. So that's helping me out there. So let's have a look at our actual code. So, well, we want the 0 page registers B and C to be the equivalent to 1000, and then we are just using push pair and pull pair, which is pushing those 0 page registers onto the stack. Now, of course, that can't be done directly. So what we have to do is we have to load them into the accumulator and push that onto the stack. Of course, it is important to notice that this will corrupt the accumulator. So in some cases, I think this get random command was up here originally, but I've had to move it down here. And then we're just filtering, restricting to a finite number of values here, because we need a value from 0 to 31. Clearing carry, adding to L, so that we've got now a column in the tile map. Then we're loading B with 0. Now this is another case where I probably really want to change this to use X because it'll be faster. But anyway, I've not done it yet. So, you know, there's still loads more optimization worth doing, because the scrolling, the Grime falling down effect is a bit too slow on some of the systems. So it does need improving. But I've not done it yet. It does work fine at the moment, and that's the most important thing. So what we're doing here is we're trying to find an X column that has not been filled all the way to the bottom, and when we find one, we load it with tile 13, which is that descending grime. Then we restore BC, but we back it up again because we need it again later here immediately. And what we're doing here is we are basically working out what sound we want to play here. So chibi sound will take a value here, and we need to make the pitch change as the grime descends. So that's all we're doing here. Again, maybe I could use some better registers here to save that push and pull, but that's probably not too bad actually, because that's kind of an outer loop, so I don't think that's necessarily as bad. And then here we're decreasing BC using this function here, and we're seeing if B and C are both 0 by ORing them together. And if they are not, then we repeat, and if they are, then we're done. We need to turn off the sound by setting chibi sound to 0 using the register here. And then we're filling the tile map. And this is the CLDIR command. Now, because this is random, it doesn't always fill the screen properly. So what I'm doing is I'm loading the entire tile map with number 13, which is that dark green grime. So here we're setting HL to the tile map. We're setting the byte count to the length of the tile map +1. We're loading the accumulator with A, and when we run CLDIR, it sets DE to tile map +1. So we've saved the commands for load DE with tile map +1, and we've saved the command to load HL with this value here. So we immediately save space the first time we use this, but this is used about half a dozen times in Grime, and it's used in some of the functions for the clear screen command and things now. So as I say, it's really going to save me some extra space. And on, as I say, the BBC 16 kilobytes of memory, once you've used up all the screen memory, you need to save that space. So that's what I'm doing. Forcing a repaint of the screen so that we redraw everything. Repainting the screen. Short delay, again using that load pair command. Then we're decreasing the lives. Now this is an interesting point. On the 6502 we can do this in a single line, but on the Z80 it was a bit more of a pain. You either had to do load HL, lives, dec lives, or load A from lives and then dec it and then save it back again. And the other thing is, you may notice a lot of the time when I was loading the accumulator in Z80, you often had to do commands like OR A to test the value within the accumulator to see if it was 0, but practically every command on the 6502 updates things like the 0 flag and the carry flag automatically. So there's none of that comparing just to see if things are 0 or not. It's all done automatically, and that does give us some savings here and there. I think overall it's still worse because, you know, all of these 0 page commands, as I've said, this is 2 bytes, whereas LDA, B would have been 1. So I think overall it's probably still worse, but as I say, in some cases it's definitely better. So here we're just locating the cursor positions. We're using our X and Y register here for our location command. We were using B and C on the Z80 systems, but because we've got an X and Y register, I decided to use it for locate here. And then we're loading the address of game over message, printing it to the screen, game over message 2. And then here we're using the binary coded decimal compare command, which I've written for the 6502, and we're comparing the score and the high score to see if the high score is high, it has been beaten, and if it has, then we have to update the high score, and we do that here. Now, one interesting thing on the Nintendo NES, the chip actually doesn't have the binary coded decimal support built into it. They took it out because they wanted to make us suffer, I guess. But I've actually written an emulator. It's only very small, but it just simulates the binary coded decimal functions that the NES should have had that they've taken out just to punish us. So there we go. That still works on the NES, which is good. So then we just here we're just updating the score, copying 4 bytes from score to high score. Very easy there, just a quick way of doing it. I think actually might not be worth using LDAR for that, but I have anyway. And then here, this is an extra bit for the links. The links title screen was too small to show the high score, so we show it on the game over screen whether they got a high score or not. And then we wait for the player to press fire and show the title screen. Here's the messages for the game over. Character 255 terminated, as always. That's what I always use at the moment. Here's my random number generator. It's not good enough. What I'm doing is I'm using the source code of the title screen. I'm using Y as an offset, which I'm using from the previous random seed, and then I'm EORing in the previous random seed, adding a few other values. It's not working well. I need to do better, but as I say, it's all I've come up with yet. I'll have a play maybe if I have time, try and come up with a better random number generator. I think it was Doom. The original source code for Doom actually had a table of 256 bytes with each number from 0 to 255 in a random order, and it was literally using a lookup table. Great if you're on a 16-bit system, but on an 8-bit system, probably not really able to use that much memory. But maybe I can use 8 bytes with random nibbles and shift the nibbles around or something. That's what I'm thinking. Anyway, as I say, I need to do better, but this is tiding me over at the moment. One big problem I was having with this in the early days, though, is when I'm dropping a descender, for example, I pick a column from 0 to 32, and if I get a column that is outside of the screen area, I pick the random number. But because my random number generation was so poor, sometimes I was never getting a valid random number, and it was just hanging the game. That was causing a lot of the crashes. I mean, not a true crash, but an infinite loop. That was causing a lot of the problems with the game halting at the early stages, and only on certain systems, because the way the random numbers were being picked was slightly different on each system. So anyway, I think we won't cover any more of it. As I say, I'm going to go over it all on the last day anyway. So there we go. So what's coming up next then? Well, I need to fix the sprites on systems like the Apple II, where the sprites are really quite nasty. The 16-colour ones are going to stay the way they are, because I was happy with those at the end of the Grime Z80. But systems like the Apple II and the Atari 5200, they need the sprites improving for the limitations of those systems, and the Commodore 64, of course. So that's going to be done. I want to do more optimization, more testing. Maybe there's a few graphical bugs here and there. I want to try and improve the SNES and the NES video output. As I said, they're not very good at the moment, so I want to try and write better interrupt managed screen refreshers for those. Code commenting, of course, speed optimization, size optimizations. But hopefully we're sort of on the home run now, and we can really just get this game finished, reliable, and well code commented for people who want to learn from it. Anyway, that's enough for today. Thanks for watching, and goodbye.